Ladies and gentlemen, it is 4 o'clock Eastern on a Tuesday, which means it must be time once again for the briefing room. Yes, indeed. My name is Eric Cavanaugh. I will be your host for today's episode, and this is cool stuff, folks. We've been talking about gamma ray guns and Mercury and retrograde all in the pre-show, and that means we're going to have a very cool and interesting program for you today. The topic is a term I use all the time, an expression, life in the fast lane. The power of large-scale graphs. That's exactly right. They're all over the place these days. There's the fight about yours truly. Hit me up on Twitter at Eric_Cavanaugh, and I'll be sure to get back to you. The mission, of course, is to reveal the essential characteristics of enterprise software. We're going to dig deep, and you folks play a big part in making that happen by asking good questions. We always get great questions in the briefing room, so don't be shy. Send them in at any time. We'll queue it up at the end of the webcast. So we do different topics every month here in the briefing room. Data science, advanced analytics is what we're talking about this week, and this month, I should say. Lots of interesting stuff going on in the data science field, obviously, for lots of reasons. One, there's a lot of data out there, a lot more data than there used to be. And, of course, much of it is spinning out of these online worlds, and especially these social engines. So LinkedIn, Facebook, Twitter, almost everyone out there uses one of these different tools, Facebook, LinkedIn, Twitter. Graph technology is baked into all of these different systems, and it's really used to help identify who knows whom, for example. Of course, LinkedIn is famous for this, and I often use LinkedIn as an example to show just how much things have changed and to give an example of the new dominating forces in the marketplace. Those of you who've been around for a while, you might remember something called the Who's Who marketplace, the Who's Who publication. Well, LinkedIn pretty much came along and crushed those poor guys. It's still out there, but you don't really hear about it anymore because LinkedIn basically owns the market. Facebook, of course, is I call it a new telco engine, really, because it is a telecommunications platform. It just allows you not just to talk over the telephone, but to share videos and to chat and to do all kinds of different things. And there's Graph underneath all of this stuff. So Graph is being used to help these businesses understand, for example, who knows whom, thereby understanding who can be your next best connection, for example, but it also can give all kinds of other insights. So we're going to talk about that in the show today. We have our very own Dr. Robin Bloor in the briefing room this afternoon. Always happy to have him here. And Blazegraph, formerly called SysApp. Blazegraph is a high-performance graph database platform. It uses GPU-accelerated plugins that do some pretty interesting stuff. And Blazegraph DASL, you can see, provides graph and machine learning algorithms for developers. So really, we've got two of the coolest technologies in the marketplace today, machine learning and graph technology. So we'll learn about both of those on our program. There is Brad Bebee. He's CEO and managing partner of Blazegraph. These guys have been out of this stuff for a while now. And with that, I'm going to hand it off to the experts. Brad, take it away. The floor is yours.
All right, great. Well, can everybody hear me? Really excited today to talk about GPU acceleration for graph databases and graph analytics. But before we get started, I wanted to kind of go into a little bit of a background about graphs and why graphs are important. And, Eric mentioned a lot of the social networking applications, but, you also need to think beyond just nodes and links and edges and vertices, beyond your sort of LinkedIn and Facebook type networks. Think about communication networks, think about biological networks, and more fundamentally, graphs represent a data structure that is very well suited towards representing complex dependencies in your data. So if you have multiple data sets that you want to correlate or do analytics over, graphs can be a very, very effective way to do that. And so graphs are key to machine learning and deep learning applications because of that. Part of the challenges with graphs is that as graphs become large and as you scale up graphs, graphs become these billion-edge structures that challenge existing computing platforms. So if you look on the right there, you'll see a map of the internet, I think circa 2006, is just as an example of the type of large, complex structure that a big graph can become. What we do is we provide scalable solutions for graphs. We have an open source platform, which is thousands of active deployments and hundreds of downloads. We have enterprise features for high availability. We have a scale-out architecture, and we're launching our capabilities for GPU acceleration. This is sort of a brief snapshot of kind of where we see the most pull in the market. We see a lot of applications in life sciences and precision medicine. This is ranging from graph-based data integration approaches to drug hypothesis regeneration techniques where you try and find existing approved drugs that can be used to treat new conditions, to cancer genomics type research. And this is a really a very exciting space and one that we've seen a lot of interest in lately. Financial services kind of runs the gamut for graph applications that we've seen. We have customers that are doing things like counterparty trading analytics. We have customers that are doing master data management type graph applications and customers doing regulatory compliance applications. The information management space is probably one of the most traditional applications for many of the information retrieval graph applications. And so in that space, you're probably familiar with the Wikidata Query Service and run by the Wikimedia Foundation. That's powered by our software. And we also have a number of other cultural and media type applications that leverage the graph database underneath to be able to improve the way they're able to deliver content. The sort of industrial and IoT applications are an emerging space. We have some long-standing OEM type relationships where people like EMC are using our software to help manage and provide situational awareness for data center type applications. But one of the things that characterizes IoT applications is they have a large amount of sensor data, and often it's very critical to be able to try and help to make sense of what's going on there. And graphs can provide higher level data structures and higher level models that you can use to aggregate. So we see these things in applications like connected buildings, power distribution type systems where you're wanting to overlay some sort of process model on top of your sensor data. And of course, cyber, both commercial and defense, as well as defense and intel applications, is a very traditional space for graphs. We've really been at this for a while. We sort of started almost 10 years ago where we were spun out of DARPA, doing some early work with DARPA graph research. In fact, our original technology was called Big Data, which was based on Google's Big Table implementation of a ground-up graph database. In fact, we own bigdata.com and have a trademark on Big Data. And over the years, we sort of developed this graph database technology. At about 2014, we really realized that, as you can imagine, having a product and a capability called Big Data in this day and age was just too confusing in the marketplace. And so we rebranded our platform as Blazegraph, which is where it is today. And then we've been working on launching our GPU accelerated features. And what's been really striking to us over the last sort of 12 or 18 months, if you look at the right-hand side of the sort of downloads chart, is just a tremendous increase in usage for our software and graph applications in general. And so we really see this as a time where there's a combination of people understanding how to apply graphs to their problem, with the hardware and the software being at a stage where you can actually take on graphs at a significant data scale and come up with meaningful results. So we see this as a very, very exciting time to be in the space. So I wanted to kind of cover a couple of the markets and spaces where we see sort of large graph problems today and emerging. And I mentioned earlier about the life sciences space. One of our customers is a company called SciAps. They're based in the Bay Area, and they have a precision medicine application where they take omics data, they take patient data, they take genetic information coming back from testing results, and they use a graph-based data integration approach to provide ways to have a common fused view of the information to help the treatment providers to be able to more effectively leverage information to be able to treat patients. Today, most of their customers that are sort of shown there have 5 to 10 billion edge graph problems. And those can reasonably fit on sort of what the types of hardware platforms that you can get from your cloud service providers today. But in talking with them and where they think they're going, they see their largest customers having 100 billion edge graph problems sort of towards the middle of the end of next year. And at that sort of data scale, you really need to look at different approaches to be able to get the performance that you need out of the graph. We talked a little bit earlier about information management. One of the great things about graphs is graphs provide you a way to represent knowledge. And so you can move beyond just doing text searching where you're finding sort of examples of a bunch of pages. And you can actually help to build information retrieval systems where you can find answers. And so that's what people are doing. The Wikimedia Foundation has taken on the Freebase information and integrated into Wikidata. They're providing that as a graph-based query service for the Wikidata query service. There's a number of very interesting cultural heritage applications that we're involved with, most notably with the research space in the British Museum, where these organizations have a mission to be able to display and make cultural artifacts available to the public, but they have a constraint in the amount of sort of physical real estate that they have in which to display the artifacts. And so they're using a combination of graph-based approaches, virtual reality, to allow people to experience many of the artifacts that they're just not able to display. So that's a very interesting graph application space. A different type of sort of life sciences, chemical analytics space is one that we just recently have been working on. And this is where they're looking at doing material science and analyzing polymer structures. In this case, they have an existing graph application. They want to take publicly available reference data, in this case the PubChem data set, which is published by the NCI. They have proprietary graph information from their research organization, and they want to be able to build portals for their researchers and scientists to be able to retrieve information about chemical compounds, to be able to help them research and develop new compounds with certain characteristics. And so they were looking at various different approaches ranging from sort of traditional supercomputing type approaches to Oracle spatial type approaches. And they found that the combination of GPU acceleration with graph databases seemed to be the right fit in this particular case. The law enforcement telecommunication applications are a very significant source of graph areas. And one of the cases that we're working with now is in a sort of a law enforcement space where you're looking at telecommunication events that are taking place in time and located in space. And the general application is that when you want to maintain some sort of rolling time window of these events indexed in time and space, and when something of interest happens, you want to be able to draw a box around the space or the center of where it happened, and to be able to replay over time and ask of the communication devices that were involved, who communicated with whom over time, to give you an opportunity to be able to apprehend and discuss persons of interest. And we think this use case is very, very relevant to a number of different sort of mobile and telecommunication-based marketing type use cases. What's important about it from a graph scale perspective is, in this case, for a modest geographic area today, for about 90 days of events, they're talking on about a 40 billion edge graph. We're handling that on a single large machine today, but they'd like to go to a larger time window and a larger geographic area. And that will drive the data scale up towards 1 trillion edges. And so, again, at that graph data scale, you really need to look at different types of computing approaches to allow you to maintain your performance. So the thing that's very unique about graphs is they don't scale in the same way that you can scale other big data challenges. And so graphs have these properties that they call non-locality or data-dependent parallelism. And so even if you have a very large graph with very, very fast CPUs, as you traverse it, you're going to have to be paging in and out of main memory. And so your CPU cores, no matter how fast they are, will end up waiting for the data to get there from memory. And so we call that condition the graph cache thrash. And so if you look at this chart here, across the x-axis, you'll see the number of access latencies per clock cycle for various different types of cache and main memory that's shown on the y-axis. And if you look towards the top, where you go from the sort of mustard-colored line all the way to the red line, you can see that you pay almost a 5x penalty when you go from cache into main memory. And this is really why existing hardware and software architectures don't scale cost effectively for graphs. They're really just not based on the right paradigm. So the first product that we're bringing out that takes advantage of this is something we call Blazegraph GPU. And Blazegraph GPU is really what we think of as a classic GPU accelerated application. So you take our existing Blazegraph database platform, which supports high-level APIs for graphs, so Sparkle and RDF, as well as the Tinkerpop Gremlin stack from the property graph space. You add a GPU and appropriate commercial licensing, and you're able to accelerate your applications by 200 to 300x with almost no code changes. This work was really started off with some research that we did with DARPA and co-developed with the University of Utah Ski Institute. But this is very exciting in terms of being able to allow you to access the performance that you can get with GPUs while staying in very comfortable and convenient graph API layers. So we wanted to look at just how much acceleration we can get from this platform. And if you're familiar with the graph space, there's a number of different graph database benchmarks. One of the oldest of them is something called the Lublin benchmark or the Lehigh University benchmark. And what it does is it has a data generator that simulates numbers of universities. And so this is looking at the U1000. So it's the Lublin generator run over 1,000 universities. And it generates simulated universities where universities have departments and departments have faculty members and students take courses and students have advisors and so on and so forth. And so U1000 is about 170 million edge graph. And the query here, which is a Sparkle query, is query number 9. There are 14 queries in the Lublin benchmark. And query number 9 is one of the more challenging conjunctive queries in the benchmark. And this query essentially says, can you find me all the students who take a course that's also taught by their advisor? And so that's what that Sparkle query looks like. And so on our CPU platform for this data scale, we get about 172,000 results, and it takes almost 54 seconds to do that. For the same query executed over our GPU accelerated version, we get the same number of results, but it only takes about 187 milliseconds. So you can see there's a tremendous acceleration possible for these kinds of graph queries. One of the common measures of graph traversal performance is what's called a gigatep, or 1 billion traversed edges per second. And so we wanted to look at the various costs in terms of hardware platforms to be able to achieve a performance of a gigatep. And so we're taking the published performance numbers and using them to divide by the total cost. And so the first number, which is a large Hadoop cluster, came out of something that's called the NSA Big Data Experiment that Carnegie Mellon did several years ago. And they looked at using a large Hadoop accumulo cluster to do graph traversals of a very, very large scale-free graph. And they did achieve nice linear scaling, but they only, the throughput they got was only in the hundreds of millions traverse edges per second. And really sort of speaks to disk-oriented systems and approaches really aren't the right way to scale graphs for performance. So now moving towards the middle, the Cray XMT2 is a popular supercomputing architecture, very elegant hardware architecture. This is based on their Graph 500 numbers, which are Graph 500 is a major published benchmark in the graph traversal space, and based on our estimate of the price of an XMT2 at the time. So our estimate there is it's about $180,000 to achieve a gigatop of performance. With what we've demonstrated on clusters of up to 64 K40s, today the traversal performance is about 16K. And with the Pascal or the P100 that was announced at this year's NVIDIA GPU Technology Conference, which does two things. It both increases the amount of bandwidth to main memory and increases the amount of memory on the card. It takes it down another factor of 4. So you can see that there's just a tremendous price performance advantage possible for GPUs on these types of large-scale graph problems. There are some other new capabilities that are very exciting for large-scale graph problems as well. And so as graphs are really, unlike many deep learning applications, graphs are very much a memory bandwidth-bound challenge. And so platforms like the Pascal and then IBM's Open Power 8 Plus architecture bring a number of different high-speed interconnects that help you to really marry up the processor memory with the GPU accelerators and increase the amount of memory that's available, as well as providing unified memory addressing, which is something that's coming in CUDA 8 with support from the Pascal. And this allows you to transparently move between the memory available on the hardware and the memory available on the host. And so we think these are some very, very exciting capabilities for very large-scale graph traversals. And of course, we're going to talk about Blazegraph Dazzle in a couple of slides to sort of give you a background about how you can easily put this speed and power to use for your applications. So we wanted to look for graph traversals and compare the performance of GPUs with Apache Spark. And so this was some work that we did this fall. We were looking at using the ICWSM 2010 Twitter followers graph. So this is about a 2 billion edge graph consisting of Twitter handles and their followers over time. It's been widely used for research. It's cited in the Spark papers itself. And so we compared it across a couple of different hardware configurations. And so the configuration shown in the green is a single fat node configuration consisting of a Xeon 2650, which had 128 gigs of RAM. And then we had two K80s GPUs, which had about 48 gigs of RAM in total. And for the breadth first search traversal on this platform, we showed it was about 1,400 times faster. But we can only process about 700 million edges of the graph fitting in GPU RAM. So we went a little bit further and expanded into a 16-node EC2 cluster, as well as expanded into a cluster of 16 InfiniBand connected K40 GPUs. So you can see the numbers there. The GPUs had about 192 gigs of GPU RAM available to them, and the cluster, the EC2 cluster, had a total of just under 500 gigs of CPU RAM. And in that case, we showed we were about 1,800 times faster for this traversal. And then we did one other configuration, and this was looking at much larger EC2 clusters, and this is the red one. So there was almost 2 terabytes of RAM on the 16-node Spark cluster versus the same size of GPUs. And so there we were still substantially 700x faster for the traversal. And so you can see that, again, just the acceleration that can be possible with this kind of hardware technology. Where we really see the problem and the challenge is making that power of the hardware easily accessible to people who understand how to write analytics. The same kinds of people that can make these high-performance, multi-core, accelerated HPC platforms work effectively and perform at scale tend to not be the same people who really understand how to write analytics that are meaningful to the line of business or to the particular mission that's involved. And so what we really see the need and the opportunity is for ways for people to express simpler and smarter algorithms that can run on GPUs and other multi-core devices without having to really get down into the challenges of doing parallel programming or working on device-specific programming languages and techniques. And so we've developed something that we call Blazegraph Dazzle. So it's D-A-S-L, and we pronounce it Dazzle. And the goal of Dazzle is to be as easy to use as Spark and Scala, but to deliver the speed that you can get for GPUs and hardware. And so it is an acronym, and so you can see why we've sort of shortened it to call it Dazzle. And what Dazzle is it's a domain-specific language that's targeted for graph and machine learning. And so it's written in Scala, and it provides a library of primitives within the DSL that we can efficiently execute in our runtime across multi-GPUs. It also supports the definition of user-defined functions in Scala, which we do code generation on and compile down into CUDA kernels that execute across the GPUs. And so by providing this relatively high-level language for you to express your analytics, we've built an abstraction layer over the hardware. But yet we're still able to generate the code to let you run at almost the full speed that we'd get from hand-tuned code. The other thing that was really important to us as we thought about Dazzle is we've understood from our experiences that it's not enough to just be really fast. You know, if you can do something 1,000 times faster, but it takes you 3 days to move your data there, you really haven't delivered a win. And so one of the things that was very important in our thinking about this platform is to be able to make it to work very closely with the existing data ecosystem. So think about Spark and Hadoop, and also, you know, as we're evolving the product, you know, really moving towards a data frames-centric view where you can do your data science in Pandas or Spark in your data frames and move very easily between data frames and the graph applications. So so that's, I think, one of the key points that we see in terms of being able to integrate this kind of hardware and speed into your environment. So what does a Dazzle algorithm look like? If you're familiar with C++ or CUDA, you won't see that here. So Dazzle really very much is a high-level Scala piece. And so if you're familiar with working with something like GraphX in Apache, you can see this is an example of an implementation of a single source shortest path algorithm, which is a very fundamental graph traversal analytic. On the left-hand side, you can see sort of the abstract base class. On the right-hand side, you can see the linear algebra-centric implementation of the SSSP. And this is the whole algorithm. And so this kind of 60 lines of code or so expresses the SSSP algorithm. We then execute that in native code underneath. And so in just a few lines, you can really deliver the power of the GPU and get the performance gains that are possible. So one of the things that we see, and this is an example of sort of a view into our product backlog, if you will, we see this sort of convergence between graph and machine learning and deep learning. And so people are building graphs, and then they use the graphs to try and represent dependencies within their data. But then they're also building certain types of classifiers, machine learning classifiers, and they want to run those over the graph, and then they're putting attributes back into the graph to be able to do a second-order analysis on. And so if you look at this from set of algorithms, starting from the left-hand side, you'll see things that are very traditionally graph. And so things like clustering, group detection, triangle counting, which Facebook does a lot, graph partitioning. And as you move to the right, you'll start to see things that look a little bit more like machine learning. So you see clustering k-means, things that look like recommendation systems, so multi-factorization, alternating least squares. And so you can see that there's really a broad range of things that are possible. And all of these are very much oriented in Dazzle context towards the sort of language of linear algebra. And so very much focused in terms of that space. So in terms of our actual product timeline and roadmap, at last year's supercomputing conference, we announced sort of Blazegraph GPU, and we started our proofs of concepts and key pilots. In December of this year, we made our official 1.0 release. This is for the GPU accelerated version of our graph database. At the GPU Technology Conference this year, we announced the first GPU accelerated graph database on-demand cloud service with our partner Cirruscale. And then the Dazzle platform was really started in our early release phase. And then at the end of this quarter, we'll be releasing our 1.1 release of Blazegraph GPU, which has a couple of important features in that it both expands the capabilities to multi-GPU platforms, and it supports the SPARQL 1.1 query language, which expands the number of features that can be accelerated. And then the second is our first sort of 1.0 general availability for the Dazzle platform. And so that's kind of where we stand with the product timeline today. So one of the things that we wanted to look at was we wanted to get a sense of how well are we doing. So we said that our goal is to be able to deliver people the ease of use of something like Spark, but to get the performance that you can get out of sort of a hand-tuned CUDA code. And so we looked at a couple of different systems and comparing to the Dazzle platform. And these are sort of three other systems. The first is Apache Spark GraphX, which you could say is probably one of the leading libraries for doing graph work in Apache Spark. It's really focused on ease of use. MapGraph, which is our own technology, which was the predecessor to Blazegraph GPU and Blazegraph Dazzle, sort of spun off of our research work. And then Gunrock, which is another platform by UC Davis that's really focused on high-performance graph primitives for the GPU. And so we wanted to look at all of these different systems. And in particular, we're looking at what is the complexity of the code to build the analytics versus the speed. And what we really saw was that Dazzle here just really does a great combination of being about at the same level of complexity in terms of lines of code for Spark as GraphX with very, very similar performance to the hand-tuned systems. And so when you look at this sort of metric of TEPs per line of code, you can see that Dazzle just really delivers a lot of performance for a very, very few lines of code. So you're able to express complicated things and execute them quickly without having to sort of get bogged down in some of the other challenges of writing native code pieces. And one of the things that practically we found is also very helpful with Dazzle as we've been working through some different cyber analytics use cases and other ones, is that because the analytics are so plastic, if you will, it's very easy to try out different approaches for what may work most effectively for a given data set. And you can iterate at a rate that is just not possible if you're dealing with C++ or CUDA to be able to execute the graph analytics. So sort of just kind of wrapping up here, we'll do a little bit of a case study of some work that we did with NetFlow analysis. And so I'm not sure if everyone's familiar with NetFlow data, but NetFlow is something that was started by Cisco. And a NetFlow represents effectively a connection occurring between a source IP address and a destination IP address. It has a start and an end time. It has a source and a destination port. There's some information about the protocol. And these things are typically collected at the boundary of corporate networks. And so they help you understand the connectivity in your networks. And net flow analysis is used broadly in the cyber space to try and help people understand what's going on in the network and detect anomalies. And so some of the challenges that are present with net flow analysis is the amount of data is very large. And, you know, just in a couple of hours of net flow collection, you can have millions of events. And if you're looking at aggregates over time, it's a very large space. And so even if you're using the very latest visualization technologies, and something that's you'll see on the right in this slide is a platform that's called Graphistry, which is sort of a leading GPU accelerated platform for very large graph visualizations. Even a tool like Graphistry can really only handle about 1 million nodes. And so if you're talking about a problem that is hundreds of millions of events an hour or more, and you want to look for advanced persistent threats that may be out there for months or years, you're going to need to have some kinds of ways to take a look and identify what portions of the network or what portions of the graph may be interesting. And so algorithms like path analysis, ranking algorithms, PageRank, SecureRank, BadRank, these are all examples of things that people are using, provide a toolbox, if you will, for people to analyze and slice this data up and then be able to get it into meaningful chunks that people can use to perform other analytics on. And so in this particular use case, which we didn't have the whole piece here, by doing a PageRank over a set of NetFlow information, we were able to find out an exfiltration point that was going on in the network. So great example of using graph analytic to be able to narrow down the potential space within the network and then provide you, through integration with a visualization tool, the ability to identify and allow the user to sort of drill down into it. And so that, I believe, is pretty much what I had wanted to kind of present today, and I'm very much looking forward to questions and dialogue. And so with that, I would turn it back to Eric and Robin.
All right, Robin, I just made you the presenter. Take it away.
Okay. I actually want, there's a lot to discuss, so I'll kind of dash through this because all I'm really doing here is backgrounding the audience that don't already know in the idea of graphics data and the web of what it is. The thing that I guess is worth surfacing is that analytics on big graphical data is really relatively recent. You know, we've been doing analytics forever on well-organized data in tables, and that's been pretty much most of what's been done. And where graph analytics has been done, it's kind of been in a niche area. Why was there never any graph databases? The closest you ever got to them really was the object databases, but they weren't graph databases. They weren't created for that purpose, and they weren't physically organized in order that you could get rapid access to data. I would say certainly misleading claims by other DBS products, particularly relational products, that they could handle the problem. They could handle the problem, but the problem is that it's you end up with a combinatorial explosion or a numeric explosion the more nodes you actually have in the graph. So while you may be easily able to handle graph with 1,000 nodes, it suddenly, at a certain point, you run into a real big scalability issue. And technology that isn't built directly for doing this starts to run out low down. Another reason is that there would have been perhaps graph databases a long time ago if there had been a big business pull for it. But the two areas of usage, government and of course the three-letter agencies, tended in one way or another to actually write their own stuff, and the same thing was happening in telco area. And those were two big areas where if there had been commercial product that would be taken off. What's happening now, of course, is that commercial product is appearing and is taking off. Not a lot of promising business cases until social networks appeared, but that's, I think, because people didn't think in terms of graph, because the more that you actually look at it, the more you realize that if you actually want to extract the maximum amount of meaning out of a collection of data, you actually have to go graphically at it for some of the stuff you want to get at. This is the database question. Why do you need a graph engine? Well, on the left you have the join of a couple of tables. And mostly what you do if you're doing analytics on these is you just pull those two tables together to materialize a view, and then you scan the view, or maybe you're just scanning the tables to get the information. And the relationships between data items are of secondary importance, and they're only there to give meaning to the joining together of two tables, you know. But as soon as you actually go through a network of data, which is illustrated on the right there, of course it bulges out and takes up as much space as it can, you actually realize that there are many, many possible relationships between pieces of data. And if you actually want to go through that walk the network and find out the meaning of relations, or you want to find out the number of different occurrences of a particular kind of set of relations, or you want to find out a group or a family of stuff, you know, then you actually realize you're going to have to walk the network. And as soon as you realize you're going to walk the network, if you ask yourself the question, well, how am I going to store all this so that I can access it swiftly, and that I can answer these questions like how many second cousins are there in a collection of people or something. You know, if you want to be able to answer a question like that, you're going to actually have to organize the data for parallel processing, because the only way to do that is to actually think of a data as being fairly randomly spread, and to be able to access it with a maximum level of parallelism. And that's why, of course, GPUs make a whole heap of sense, because they're great at parallelism for actually doing this. So that's why you need a graph engine. A graph engine and an engine, whether you're talking about a NoSQL or a SQL database, those engines are just not the same at all. Triple store, I just thought I'd mention this because it generally is mentioned when the whole thing of graph comes up. The work that the I know W3C committee did in terms of the definition of semantics for the World Wide Web, so what people were calling the semantic web, was to create this idea of a triple store with RDF databases that held data in triples, and as far as I know, theoretically, pretty much all language can be represented, all data can be represented using triples. That doesn't mean that an RDF database is the best organization of data for a graph, but it does mean it's pretty good, a pretty reasonable start, because you could, in one way or another, think of ways of making it good for parallel access. So an RDF database is a graph database, but a graph database is not necessarily an RDF database. The Graph Business Act, well, Brad's been through this already, so I'll not say much, but basically communication networks, yeah, there is data that you need to walk across, transport networks, data you need to walk across. MDM's ontological structures of meaning, even if they're only related categories, very, very good to go at that with graphs. Social graphs, obviously, and that brings in policing, fraud detection, all other sorts of things. The biogenetics, genome, personalized medicine, I think Brad mentioned that. Semantic applications, in the sense that you can actually, in one way or another, reduce text to a whole series of graphs, and you can walk that. And then you've got these kinds of that in the last bullet point here, these kinds of questions or the kinds of patterns or means or things to look for. What is central to something? What is the point from which everything ripples out? What are various paths? What are the patterns of paths? What are the different paths that get taken? What are the communities within any kind of structure? What are the subgraph patterns? What are the aggregations of all these things? I mean, that's the kind of thinking that goes into graph. And if you actually look at the various business applications that are mentioned above, you realize in one way or another they actually need to know or they need to look for these kinds of things. So prognosis, I would say that graph applications seem to be in their infancy, and particularly big data graph applications. But, having just sat through Brad's presentation, I have to say I was incredibly impressed with what Blazegraph are doing. So some basic questions, I'm onto questions now, but to be honest, I'll actually just shoot from the hip because I wrote more questions down than I actually had. Could you explain, Brad, just the open source nature of Blazegraph? My impression from your presentation is what you've got is a graph database that you've made open source and that it runs on a combination of CPU with GPUs, right?
Yeah, so we have a couple different platforms. So we started out with having only an open source platform, and so our core graph database platform, which provides support for the Semantic Web, Sparkle RDF, and the Apache TinkerPop stack, is available in open source under the GPL v2 license. Our early work was also in DARPA-funded work in GPU acceleration. MapGraph is also available under an Apache license. And then what we've done now with our sort of 2.0 release is we've provided enterprise features on top of sort of the open source community edition. So those features include our high availability architecture, our scale out architecture, and then also our GPU acceleration for Blazegraph. And so you can use the same APIs with our open source version, but when you want to use the GPU accelerated features, that's when you sort of move into a commercially licensed piece. And we do a lot of evaluations and things with that.
Okay, so you can download this and play with it and become familiar with it without actually needing to pay any money. But as soon as you actually want to get serious about doing something, and particularly GPU, I mean, I think that's probably a reasonable metric of people being serious is that they're wheeling in GPUs. The figures that you gave, Brad, 200 to 300 accelerator on a job run without GPUs. What's interesting me here is, and I know it's difficult to explain or to actually even put on a slide, but there are two reasons why you would be using this technology. One is that you had queries that you wanted to go a lot faster, but the other is that you actually wanted to reduce the hardware footprint involved. Now, can you actually speak to the balance of those two advantages?
Yeah, so let me start and talk a little bit about the kinds of queries that are accelerated. And so the performance lift that you're getting from the GPUs on graphs is largely about memory bandwidth advantages. And so the types of queries that are going to benefit the most are these conjunctive queries that are going to have to touch a lot of data to be able to execute the query evaluation plan. So those are the kinds of queries, where we see the greatest GPU acceleration. And so it is possible to sort of download and fully get started with the open source version. And then when you reach a point where you have problems that you want to either, as you say, they're either taking too long or another case is that you want more of a real-time type response. And so those are cases where you might take a look at moving to onto the GPU side for the graph database piece.
Okay. In terms of Dazzle, and I'd like, I can probably, in one way or another, I can probably, because I spent a lot of time with language, I can probably deduce some of the things that you're doing with Dazzle. But in terms of the targets, in terms of machine learning, because you put Dazzle up and you've got on the one hand you've got the various graph queries you can do with it, and then you've got marching all along there things that are actually nothing to do with graph or needn't necessarily be anything to do with graph. So the question really is, have you created this language in order to cover a whole series of analytics capabilities, all of which are going to obviously profit dramatically from good parallelism? And the graph is just a part of it. Is that what the target was?
Well, I think we started off with graph, and then there's been a lot of work, both historically and in particular in the last couple of years, really looking at graph and graph analytics in the context of linear algebra. And as you mentioned, GPUs are great at parallelism. So once you can take a problem and put a linear algebra spin on it, then you can take advantage of an entire ecosystem of software and hardware that is designed to really take sparse matrices and make them run very quickly on GPUs. And so really what Dazzle does is provides that sort of a front end to access use the power of linear algebra for graphs. And in doing that, we realize that there's a lot of other data analytics that people want to do that are expressed in a very similar way. And so that's kind of how we got into this sort of broader swath of things other than just traditional graph.
Yeah, and I kind of salute it, but it raises the question as to, let's say, are you expecting, well, I mean, I don't know what you're expecting. You've just created a capability, so I guess people do what they do. But, do you have in mind the idea that, yes, you'll have the Blazegraph database underneath, but there might be other databases that people actually stick across these same nodes and use Dazzle on those? I mean, is that how you're thinking of it, or have you just provided it and let people do what they will?
Well, we sort of see three different scenarios. One is a Dazzle-only scenario where someone has their data, in some other data lake or in some other system, and they just want to use the Dazzle features to be able to express analytics and run them on the GPUs without, having to actually hand code things. And so we see that as one use case. We see the GPU accelerated graph database standalone as its own use case as well. And then we see a hybrid use case where people want to, they have a need for transactional management of their graph data, so they want a graph database, but they also want to run graph analytics over that data. So they want a way to express iterative graph analytics. And that's really where we see the Dazzle and the Blazegraph GPU platforms converging.
Okay, well, that's interesting. I'm going to have to hand you back to Eric, who's got questions from the audience. But I have to say, I'm going to actually have to think deeply about Dazzle because it's a product in its own right. Yeah.
Yes, for certain. Dazzle's very interesting. So we've seen quite a lot of interesting things with Dazzle.
Good stuff. Well, let me throw some questions at you from the audience. So we have some good ones, as we always do, and thank you, folks, for sending these in. So here's a good one. An attendee asks, when graphs are used for information retrieval, don't they require careful preparation upstream, which is contrary to simpler engines, which will just apply automatic full-text indexing and so forth? What do you think about that?
Yeah, I mean, so certainly managing and curating knowledge for these kinds of knowledge-based information retrieval systems is a big part of what makes them effective or not. So I think I would agree with that. That there's a there's different approaches to it. I think that it really depends on what the system is trying to do. With a knowledge-driven system, you can answer different kinds of questions than you're going to be able to answer through something that's just a text-indexed type capability.
Mm-hmm. Yeah, per Robin's graph too. That's a good point. Now, here's another good question. One attendee is asking: Do you have to use specialized visualization tools to take a look at this, or can you kind of plug and play other more traditional types of visualization tools to take a look at the results of what you guys can deliver?
Yeah, so we don't actually offer any visualization capabilities ourselves, and we partner through all of them. What we really try and focus on is being able to support effective data interchange. And so, in the GPU platform, we have the Sparkle endpoint, and we support all of the different graph serializations that go along with the RDF semantic web stack and the property graph stack. And then on the Dazzle side, we're really moving towards the sort of data frames and RDDs, in addition to other sort of APIs to get at the data. So, from our perspective, we really want to execute the analytic and then get the result back in a place where you can then integrate it into your downstream process, whether that's a visualization like Graphistry that I showed, or whether that's another analytic that might be outside of the Dazzle platform.
Okay, and we got a couple other very specific questions here. I'll just kind of throw some of these at you. One of the questions is, when choosing the GPU, do you consider using FPGAs as well? Can you kind of talk about that for a second?
Yeah, so we've looked at FPGAs. We have looked at some other kinds of multi-core accelerated platforms, other non-NVIDIA GPUs. I think that we looked at, about 18 months ago, when we were really looking at large-scale breadth-first search, we looked at some of the results that people were getting with FPGAs. And at the time, the types of speedups we were getting were about equivalent. Certainly, we're interested as strategically in supporting a number of different hardware acceleration platforms for our software.
Okay, that sounds good. And with respect to the SciOps precision medicine use case that you talked about, an attendee is asking, can you explain a bit more about what is being modeled as the vertices and the edges?
Yeah, so their use case is at the core of it, it's a relatively classic graph-based knowledge data integration use case. And so what they have is they have essentially a SciOps precision medicine platform data model, and then they use a graph approach to be able to map all of the different data providers' information into this precision medicine data model that they provide. And so they allow you to then query the patients and patient record attributes, and then relationships between patients and treatments and those kinds of things.
Okay, good. And we have some questions around benchmarks. Do you guys wind up competing in benchmark activity? Can you kind of talk a bit about that, like how you perform against other similar platforms?
Yeah, so we are pretty active in the benchmarking space. We're members of the Linked Data Benchmarking Council, along with almost all of the graph database vendors, so Neo4j and Oracle and Virtuoso and LinkerGraph and those sorts of folks. And so we participate in that. We use benchmarking as a development tool, so we run things like the Berlin Sparkle benchmark or the SP2 benchmark as part of our development process. And then, from time to time, we do participate in benchmarking activities that people, sometimes it's university-driven, sometimes it's driven by other factors. But yeah, we're definitely interested in participating. Benchmarking is a tricky thing, because each benchmark is really designed to test something different. And so, we think that one of the things we're interested in is looking at, benchmarks that will really show off places where the GPU acceleration for graph query can bring the most potential.
Okay, and you talked a bit about algebra. One of the attendees is asking which linear algebra engine are you using in that example?
So we basically used our own implementation of linear algebra operators in the runtime.
Oh, okay. Okay, that sounds good. And this obviously, I mean, you guys are talking about large-scale graphs. So this is for solutions and challenges that are at scale, right? When we talk about organizations like LinkedIn and Facebook and Twitter, those are whole different worlds of complexity because of the magnitude of the size, right? Because of the scale of those kinds of solutions, and that's where you guys really excel, right?
Yeah, you get more benefit from as the data scale increases, you see more performance benefit from the memory bandwidth advantages. But we do offer, we do work on a single GPU version, and you can get quite a lot of performance out of a single GPU piece. And so, but really, we're targeted at really providing solutions for graphs at a larger scale, because we think that's something that's not there in the marketplace. That being said, we are really the first and only GPU accelerated graph database in the market, and there's a number of, if you look at the new, for example, Tesla M40 card, which has 24 gigs of RAM on a card, you can fit a 500 million plus edge graph problem into a single GPU, and there's a large number of graph problems that fit into that space. And so I wouldn't discount the smaller graph problem space, but we do aim to tackle both.
Yeah, I threw up this last slide here on cyber defense, because that is such a huge issue these days, and it seems to me that companies who are not appreciating the extent of the threat these days are basically begging for trouble in the near future. Can you talk about how this kind of technology can play into cybersecurity and threat assessment and threat analysis and threat detection and basically threat prevention?
Yeah, so this work is sort of some examples of things that we're doing with a large consulting firm at the moment. And they're looking at how do we apply, in particular, GPU accelerated analytics technologies to be able to detect network anomalies and do more, enable people to sort of stream through the number of false alarms and that you're getting. So if you think about, if you have even less than a 1% false alarm rate, but you have the sheer rate of network events that you're getting from a large organization, it's just overwhelming to any kind of analyst team. And so you need to be able to look at how can you use some of these other analytic techniques to be able to sort of effectively give people the tools to find things and help them to focus where they should spend their time looking.
Yep. Okay, this is great stuff, folks. Well, we do archive all these webcasts for later viewing, so feel free to come back anytime and check them out. It takes about a day usually for the archives to go up. But a very big thank you to our own Dr. Robin Bloor and to Brad Bebee from Blazegraph today for their time and attention. And we do keep all these questions and pass them on to the presenters. I know there's a couple questions we did not get to, but wow, this is good stuff. And like Robin, I'm going to have to put the thinking cap on to dig deeper into how all this stuff matters and what implications it will have. Graph is certainly a hot space, and when you combine graph with machine learning, you can see there are lots of different possibilities for how to optimize business processes, find solutions to complex problems, and I have to say the problem set is getting more complex by the day. So with that, we're going to bid you farewell, and we'll catch up to you next time, folks. We have another webcast tomorrow. Lots of hot technologies webcasts these days. Hopefully you can join us for tomorrow's webcast. And with that, we're going to bid you farewell. Take care. Bye-bye.